What is an advantage of using a constant in a linear regression model if OLS is applied? First of all, note that by constant they mean the intercept term, which you can see over here is denoted by beta 0. They have not told us whether we are working with simple linear regression or multiple linear regression. However, it is not going to matter because the essence of the question is not affected by that. Okay, so I can just assume that we are working with simple linear regression, that is something like this. Now, the reason I have written these assumptions over here because I'm going to use these assumptions to rule out some of these options. So first of all, let's take a look at part C. It says using a constant results in an unbiased OLS estimator. Well, this is not correct because the unbiasedness of the OLS estimators has nothing to do with the presence or the absence of the constant. It is basically dependent on these three assumptions. Okay. Similarly, part number D is not going to be the correct answer because the distribution of the OLS estimators in large samples is also dependent on these assumptions. So part C is ruled out, part D is ruled out. Now, if you take a look at the part A and B, there is just one word difference between these two parts. In the A part, we have using a constant results in the average of the errors being equal to 0. And in the B part, we have using a constant results in the average of the residuals being equal to 0. So first of all, let's understand the difference between errors and residuals. By errors, we mean the population error. That is this UI that you see over here on which you see this assumption as well. So this implies the meaning of the part A is expected value of U is equal to 0. Okay. And the meaning of the residuals is the sample counterpart of the population error. Basically, the residuals are denoted by U hat. So the part number B implies that the average of the U hat is equal to 0. So I hope the distinction between the part A and part B is clear. The first part is talking about the average of U and the second part is talking about the average of U hat, where U hat is known and U is unknown. Okay. So out of these two parts, which one is going to be the correct answer? Let's see. Once again, the part A is relying on these assumptions that you see over here. Specifically, if you take a look at the assumption number 1, that is expected value of UI given xi equal to 0, I can use the law of iterated expectations and from here, I can prove that the expected value of UI is equal to 0. I'm not showing you the law of iterated expectations over here because that's not the purpose of this question. However, this should make it clear that even part A cannot be the correct answer because it relies on the assumption number 1 because we can go from here to here using the law of iterated expectations. So that means the correct answer is going to be part B. So this is how you can find the answer to this question using the elimination method. But let me also show you that how can I prove that the average of residuals is going to be equal to 0 if we have a constant term in the model. So now let me prove part B mathematically. Let's assume that we are working with a simple linear regression model and a simple linear regression model can be written like this. This is the population equation. So I'm going to write over here that this is the population model and we can also write the sample counterpart of this. The sample counterpart of this is going to be yi equal to beta 0 hat plus beta 1 hat xi plus ui hat. Okay. Now we are using the method of OLS which says that we have to choose the estimators beta 0 hat and beta 1 hat such that the sum of squared residuals is minimized. Such that sum of squared residuals. So that means summation of UI hat square is minimized. Okay. And the reason we have to choose two estimators over here because we are given two parameters. In this case, the two parameters are beta 0 and beta 1. Our focus is going to be on beta 0 because that's the constant. So beta 0 hat is the estimator of beta 0. Okay. And now we are going to see that what is it that needs to be done if you want to figure out an estimator of the constant term. So if you want to figure out beta 0 hat, right, which is an estimator of beta 0, the entire attention is towards the constant because the question relates to the use of the constant in the model. So now let's see how can we do it. First of all, before we do the derivation, we need to figure out what is summation of UI hat square. So I can figure that out from the sample equation. So from the sample equation, I can write that ui hat is equal to yi minus beta 0 hat minus beta 1 hat xi. And if this is how ui hat is defined, then the summation of ui hat square is going to be summation of yi minus beta 0 hat minus beta 1 hat xi whole square. Okay. Now I'm going to differentiate this with respect to beta 0 hat. And once again, I'm not going to do the differentiation with respect to beta 1 hat because the question is going towards the presence of the constant. Okay. So we are going to find the estimator of beta 0, that is beta 0 hat. That's why we are going to see the differentiation with respect to beta 0 hat. So if I do a partial differentiation of summation of ui hat square with respect to beta 0 hat, I'm going to get 2. So this 2 that you see over here, this will go in the front, times summation of yi minus beta 0 minus beta 1 xi. So we should also put a hat over here. So this is beta 0 hat and beta 1 hat times the differentiation of the term inside the bracket. This is due to chain rule. So we have to multiply this with the differentiation of the term inside the bracket with respect to beta 0 hat. So the differentiation of this. Okay, I hope this is clear. This is basic differentiation, and then I have also used the chain rule over here. So once I do this differentiation, I'll get 2 summation yi minus beta 0 hat minus beta 1 hat xi, and then this differentiation of the second term is going to be 0 minus 1 because the differentiation of beta 0 hat with respect to beta 0 hat is going to be 1, and then the differentiation of this part is also going to be 0. So this implies that the partial differentiation of summation of ui hat square with respect to beta 0 hat gives 2 times summation yi minus beta 0 hat minus beta 1 hat xi multiplied by minus 1. So we get a minus 1 from here. So because it's multiplied by minus 1, I can just write a minus 2 over here. Okay, so I can multiply this 2 by minus 1. So it becomes minus 2. To solve for beta 0 hat, we have to put this first order condition equal to 0. So I'm going to write minus 2 summation yi minus beta 0 hat minus beta 1 hat xi equal to 0. Now this is the equation where you need to focus. So this equation can also be written as summation of yi minus beta 0 hat minus beta 1 hat xi is equal to 0. Basically, you can go from here to here by dividing both the sides by minus 2. And if you keep on solving, you will get beta 0 hat, which is an estimator of beta 0, is equal to y bar minus beta 1 hat x bar. Ideally, we are not interested in solving for the beta 0 hat entirely. What we were interested in is this procedure. Because when I was doing this differentiation procedure, I end up getting this, right? And if you notice this part carefully, this term inside the bracket is nothing but ui hat. You can see the definition of ui hat from here. It is equal to yi minus beta 0 hat minus beta 1 hat xi. And this is the same thing that we have inside the bracket. So basically from here, we get summation of ui hat is equal to 0, which means that the sum of the residuals is equal to 0. So once again, if you see whatever I have done over here, so I started with the model with a constant term, that is beta 0. Now, because you have a beta 0 in the model, we have to look for an estimator for beta 0, which is going to be beta 0 hat. And while we are deriving the formula for beta 0 hat using the method of OLS, in between that, we end up getting summation of ui hat equal to 0. Now, note that the summation of ui hat equal to 0 is not an assumption. We were trying to find the OLS estimator of beta 0, and within that procedure, we get summation of ui hat equal to 0. And I'm sure you know it very well that if the sum of a variable is equal to 0, then the mean of that variable is also going to be equal to 0. So in this case, we end up getting summation of ui hat equal to 0. That means the sum of residuals equal to 0, which implies that the average of the residuals is also going to be equal to 0. So part B is the correct answer, and this is the mathematical proof of that.